There you go. So psychrometry problem from last winter. This problem, multiple parts, goes all the way to F, A, B, C, D, E, F, is based on ideal gas mixture of water and air, and use concepts of psychrometry. That problem was worth 25% of the final exam. So to answer Jason's point, imagine 4 problems like this on the test. And really, I think once you look at it, you could kind of do it much faster than that, I would say. But you kind of have to understand, what each individual parts are. And even if you can't get the whole thing, you should be able to get pretty far, I think, going through it. So let's look at it together and let's try and solve it together. I'll turn it over to you to sort of guide me through the qualitative solution process, at least. So what we're dealing with is a big box that contains a water-air mixture in it. System is closed, so nothing can go in and out. And since it doesn't tell us that specifically, we probably should make that very clear in your list of assumptions if you want to make that assumption or not, right? So part D there is listing all the assumptions that you're making through this problem-solving exercise. And as you know, I'm pretty keen on that. Let me see, I do have my solution key there for when I did this before. So I can tell you exactly what I'm talking about. Yeah, so for a problem here, that was worth 100. This assumption is worth 20. So it's worth literally a fifth of all the points is listing your assumptions. So pay attention to that. That's always important. So I've got this box of air, moist air in there. And I'm telling you exactly the mass of the air and the mass of the water. Kind of convenient, 1 kilogram of air, right? Because the humidity ratio chart in the psych chart goes by kilograms of dry air. So now all of a sudden, my humidity ratio is just the actual mass of water I got in there. So that's kind of nice. So 7.5 gram of water per kilogram of dry air is what my initial humidity ratio is. And then suddenly, while I'm at steady state like that in that box, I'm dropping a cube of steel, a block of steel. You can imagine an industrial process where similar things could happen, right? That cube of steel has standard engineering properties. I just pulled off from engineering toolbox or somewhere. And what I'm telling you is that it's initially at minus 10 degrees Celsius when I drop the cube inside that box. Now remember, my moist air is at 20 degrees Celsius, so immediately I'm going to have a heat transfer effect taking place. I don't know the size of that cube of steel yet, but I know that when all is said and done, it sucked in 20 kilojoules of energy from the air inside the box. All right, straightforward so far, it seems to make sense. After it's done absorbing that kind of energy, the entire system's at steady state. Okay. So using a psych chart, I'm specifically asking you to use a psych chart to solve this problem here, so there's no ambiguity. And assuming, as one of the things you're going to assume, that the total pressure remains constant inside the box, what is the size of the box that we're dealing with, the dimensions of the box, the volume inside which this moist air mixture is at. Once you reach the second steady state, after dropping in the steel block in there, is there liquid water in the box? In other words, did you absorb so much heat that you're now condensing the water or not? If you're not, then presumably the relative humidity of the air inside the box is simply gone up, right? Because you drop the dry bulb temperature of the air. What's the size of the cube of steel that you dropped in? By size, I mean the mass. Okay. Of course, with the density, you could tell me what volume it is as well, but I'm just specifically interested in the mass. We've already talked about the need for outlining all our engineering assumptions. And furthermore, I want you to sketch the process on a little psych chart diagram sketch that I'm including in the test. All right. Now, of course, in your case, this being COVID and you haven't access to a computer and all, you could take the actual psych chart and annotate it, cut and paste, and drop that into your solution package. And of course, that would be perfectly acceptable and arguably preferable because you've got your actual data right there as opposed to a sketch. But we'll do both. Finally, at the new steady state, at the end of this process, give me the mass and temperature of the air in the box, the mass and temperature of the water vapor in the box, and the mass and temperature of the liquid water if you determine that there's been some condensation taking place inside the box. Finally, give me all the data for the moist air that we end up with at that steady state. Okay. Now, like every problem like this, there's easy parts and there's harder parts. And a really good strategy during test taking is to start tackling the easy parts and kind of getting a whole global view of what a problem is really going after. So I would argue that you probably are better off bouncing around the different subsections of the problem as opposed to going sequentially. Part A, what does part A ask? Like, and put your nose to the grindstone immediately, attack part A, then part B, then part C. And I think there's a natural human inclination to doing that. You just want to go sequentially because you don't want to make sure you don't miss any part. But I strongly advise you, not just in this class, but in all the class that you'll be taking when you do these tests in the next couple of weeks, to take the entire test and read the entire thing without even holding a pencil in your hand. Just read the entire thing. And a big reason for that is while you're doing that, the wheels are turning subconsciously while you're doing that. And you're not even realizing, but you're already establishing a roadmap for problem solving for the entire test. Then when you go back to each individual problem, you're still in the back of your mind processing the other problems that you've already read. And while you're very focused on this one little element, when you go back to these other sections you've already read, lo and behold, you've got a game plan and you didn't even know you were planning for one. Well, on a smaller level, you're doing the same thing on an individual problem by having read every single parts of it. So let's start with that. I would argue that the first thing that I would do if I saw a problem like this is start thinking about part E, the sketch of where I'm at initially, my initial steady state, and where my final steady state might be. Even if I can't say quantitatively exactly where it's at just yet, because I haven't done enough analysis, I want to get a good feel for where I might start and where I might end. So it's telling me that I've got 7.5 grams of water at 20 degrees C and a kilogram of dry air initially. So, and it's telling me to go to a psych chart. So step number one is I'm going to go to that psych chart and I'm going to figure out exactly where I am to begin with. I'm going to note right off the bat that I'm initially at steady state. In other words, there's nothing funny going on there. Initially at steady state, and finally, I'm going to be also at steady state. It's a little bit stating the obvious, I think, but it's not bad. Not a bad process to do that. Just so that you're clear what it is that you're trying to approach here. So it's a transient problem, and we're going from state 1 to state 2, and both of those states are 2 different steady state points. Okay, that's what we're doing. Okay, we're also going to assume that the system is closed, because the box isn't specifically saying that it's, that nothing can go in or out. So that makes, because it's insulated, it makes it an isolated system. All right, an isolated system is a closed system that does not interact with its surrounding. And this is not interacting with its surrounding, either energy-wise or mass-wise. So we're that's another clear thing that we're assuming at this point. Anything else that I want to say at this point? We're kind of in good shape, right? Just so we're clear here, when we're going to go to the psych chart is going to give us lines of constant relative humidity that are going to look kind of like this. These are phi is equal to constant. This is the humidity ratio, which is going to be in kilojoules per kg of dry air, which I'm going to abbreviate as DA. Okay. Oops, sorry. No, it's not kilojoules, right? What is this?
Is it like grains?
Yeah, grains of water or mass of water. In a metric system, I think it's going to go with kilograms of water, even though the numbers are going to be very, very small. Okay, kilograms of water per kilograms of dry air. And in this particular case, it's telling us that I'm at 7.5 grams of water in the box, which means that I'm going to be at my state 1 somewhere here. 7.5 kilogram is 0.0075 kg of water per kg of dry air. So I'm somewhere on that curve here, on that straight line initially. My 0.1's got to be in there somewhere, okay? I'm also going to have lines that are going to be kind of like this. Right, those are going to be my constant wet bulb temperature and constant enthalpy curves for different values. If I remember correctly, my psych chart is also going to have steeper curves that are going to go like that. And those are going to be lines of constant specific volumes. You know, it doesn't hurt to kind of think about what the psych chart looks like as we're working out through these problems. And I'm writing down these things because obviously, since I'm exchanging energy between a steel block and that air, this is going to be a conservation of energy problem. So the enthalpy is going to be important. I remember that part A of the problem, at least, is asking me for some sizes. So the specific volume is going to be important. So I'm writing down these things knowing that they're probably going to be important as I'm moving along on this problem here. In that manner. You know, this is an axis for dry bulb temperature. And I know that I'm at initially 20 degrees Celsius. So presumably I'm, you know, 20 degrees Celsius is going to intersect that dashed red line somewhere. But before I stick my neck out on that one, let's just take a look at the psych chart and see what that should look like. Okay. So let's do that. And I've got my psych chart ready over here. So I'm going to share that with you. And voila, just like you know, I've got my copy of the book. If you have an electronic copy of the book, that'll be really convenient for the final exam because you can just cut and paste images from your computer book to whatever you're going to submit to me. I like that, but if you don't, no problem. Just grab the real book and work with that like you would at Cap Poly. All right, so here's my omega scale here. Humidity ratio, kg water per kg of dry air, just like I expected, right? And I said 0.075, 0.08, 0.06, 0.07. So this is going to be this line right there is what I'm looking at. So I'm moving horizontally along that line. And I keep going until I'm at 20 degrees Celsius, right? This guy right there. So here I am. This is the point. That's what I'm after. Awesome. Okay, so that's my 0.1. I'm at steady state. Before I drop the chunk of steel in that box, I'm exactly there. So what I would do at that point myself is I would label my state 0.1 on my diagram. So I'm going to do that for myself. We'll go back to it later, but you're probably doing the same thing yourself. What color? I'm going to pick a different color here. There we go. That's my point 1. And while I'm there and I'm looking at this, might as well write down the state properties, right? Because I figured out where I'm at. Might as well highlight what I got here. So state properties at 1. What do I have? You guys help me out here. Phi. What's my phi?
50.
What's my V1? What's my H1? Start with that. And what's my T wet bulb? All right, go for it, Nicholas.
It looks like phi is 50.
It looks like what, sorry?
Phi is 50.
Phi is 50. Yeah, right, exactly. So this is a nice, I picked a nice point here, right? Because the data is relatively straightforward to catch. Here's the lines of constant phi, and he's right. Nicholas is right. It looks like about 50%. And that means that my relative humidity is at 50%. That means that I'm at roughly half of the water amount in the air that I need to saturate the air, right? So I'm at that point right there. That's 7.5. If I go straight up, I should be at about 15. If that's correct, boom. Yeah, look at this. I'm at about 15. So I got roughly half of the water in the air that I would need to fully saturate the air. So yeah, that sounds good. Phi is 50. What else? And I'm not saying I need all this information. What I'm saying is I'm doing all this effort to pinpoint where state 1 is. I might as well put a little box on my chart right next to it and start boom, 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 boom. It's not taking me any time to do this, and I'm done. I got the darn data. So not a bad strategy here for problem solving. What else? Tell me everything you can about this point right there, which is my point 1, my steady state point 1. At this point, you should be able to move pretty fast.
It looks like specific volumes, 0.84.
I agree with you, 0.84. And that would be meter cube per kg. All right, and Dylan's telling us that because he's looking at this 0.85 right there, and the steep lines correspond to specific volume. It says so right there. This is 0.9, this is 0.85, this is 0.8, and I'm right there. So that's 0.81, 2, 3, 4, boom, that's where I'm at. Okay, I'm with you. Next. Nobody.
The enthalpy is 39 kilojoules per kilogram.
Enthalpy. So the enthalpy are the less steep curve. So there are these. Go for it. Sorry, I'm blocking you here. Go ahead.
Sorry, I think I might have traced the wrong line when I was.
Well, let's take a look. Let's say enthalpy is a good one to look at. So these less steep horizontal line are going to be the lines of constant enthalpy, right? And if we want to make sure of that, well, it says specific enthalpy right there, and these curves are going straight through like that. So we are here. So I'm going to follow this curve right here, and this horizontal line, by the way, is really the line of constant wet bulb temperature, which itself is parallel to the lines of constant enthalpy, as you saw when you were doing your reading. So I'm simply extending that curve over to the enthalpy scale, and that's where I'm hitting. And it looks like that's 30, 32, 4, 6, 8, and I was right there. So it's 39 kilojoules per kilogram of dry air. I think that's what he said. Anyway, I'm going with that. That looks good to me. 39. Okay. All right. So I've got the enthalpy initially. That's got to be an important one because we're going to do a conservation of energy analysis on this. What else? Well, we just said, you know, the wet bulb temperature is that line. So why don't we just mark that down just for giggles here since we're there. That's 10. That's 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, these are funny lines there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these ones are the lines of constant dB and a wet bulb WB. So I'm on this one. So that looks like 14 degrees Celsius, my wet bulb temperature. So even though the air is at 20, if I had a sling psychrometer like we saw before, I would expect the one with the wet gauze on it to read 14 degrees Celsius is what we've established there. Okay, all right, I think I got all I'm going to get out of that chart, right? We're good. So let's think about physically the process of what happens at state one. We're at steady state. We're going to stay at that point forever unless something happens. And we quickly open the box and we drop this block of steel in there, and that block of steel is absorbing 20 kilojoules. So what physically happens when you do that? What does that mean on the site chart, sucking 20 kilojoules out of that air, right? That energy's got to come from somewhere. It's going into the steel. It's coming out of the moist air. So plot me a curve on that site chart that illustrates this, somebody.
Would you decrease the enthalpy by the amount of energy absorbed?
Yeah, I think that's a good way to look. I mean, right, the change, we're going to do an energy balance very soon. And that energy balance is going to tell us that the change in energy, because it's energy we're dealing with, of the steel has to equal the change in energy of the air, because that's where the energy is coming from. All right. Our pressure is relatively constant. Nothing else is changing much. So all that change in enthalpy is really coming from the internal energy of the air. So delta U is approximately equal to delta H of that air. So we're going to be looking at a change in enthalpy of the moist air, a change in enthalpy of the moist air. And yeah, so we're going to be tracing a change in enthalpy of the moist air. What does that look like on the site chart? What is the direction of movement that I'm doing? Like, these are lines of constant enthalpy. So are we like moving this way, like normal to those lines? Is that what we're doing? What are we doing?
Is this a constant humidity ratio, right?
Constant humidity ratio. So
the masses aren't.
Y-axis constant?
Yeah.
All right, so Nicholas is saying that I'm starting here at 7.5 and I'm going to stay on that horizontal line, either left or right. So which side am I going, Nicholas? Am I going left or right for that air?
Left.
I'm going left because that's the direction where the enthalpy is dropping, and I'm sucking that 20 kilojoules out of the air. So the enthalpy of the air has got to drop. Correct. Okay, exactly. So I'm going to move to the left, which means that the relative humidity ratio is increasing until eventually I hit that guy right there, that point right there. What does that point tell me?
The moist air is saturated.
Exactly. Yeah, that's the point of 100% relative humidity at that point. So the air is saturated. It's about to rain. That's what it tells me. Okay. Is that where the game ends? We're done at that point? If we reach that point, we're done? Well, we could be if to go from point 1 to that point, suck 20 kilojoules or less of energy out of the air, then we're done. Okay, we might not even get there. I mean, it's possible that we stop here, right? We could stop here if the amount of energy taken out of the air between this point and that point is 20 kilojoules, we're done. All right? Or we might get all the way here. And maybe to get all the way here, we haven't taken out 20 kilojoules of energy out of the air yet. Does that mean we're going to stop taking energy out of the air because the air is saturated at that point? What else happens?
The water condenses.
At that point, once we reach that point, if there's still more energy to be absorbed by the steel, and how are we going to know if there's still more energy to be absorbed by the steel?
Looking at the specific enthalpy at that point.
Yeah, that's right. And therefore the total enthalpy being absorbed by the water. But more importantly, like as this process is taking place in a transient way, right? The steel temperature keeps going up and up and up and up. And the air temperature keeps going down and down and down and down and down, right? Because as we're moving from point 1 to the left, the dry bulb temperature, and that's the temperature that the thermometer in the air would tell us, keeps going down. By the time we're here, we're at about 10 degrees Celsius. The steel start at minus 10 Celsius. If the steel is not at plus 10 Celsius at that point, we're not in equilibrium, right? The steel is still too cold. There's a difference in temperature between the steel and the air. The steel is going to be absorbing energy. That's how that works, right? Energy is going to go from hot to cold until the equilibrium is reached. So we're going to start condensing water past that point. So we're going to keep moving to the left, but now we're going to move on the line of constant relative humidity, saturation, and we're going to keep going down that curve until the total enthalpy of the air-water mixture is dropped by exactly 20 kilojoules. At that point, based on a problem statement, the steel is absorbed, all of the energy is going to absorb. That make sense? So you see, we kind of talked ourselves into the whole process here, mostly by words, without even, no fancy complicated equation here, just basically a philosophy of conservation of energy, what's going on inside the box. We spent a lot of time doing that, but now let's put some pencil to paper and quantify everything that just happened. And I'm going to go back to the other computer to do that so I can start sketching things up. And hopefully that makes sense to you and you agree with me on it. And if not, just let's just talk about it. Okay, so back to my point one. So what we just said is that, all right, I'm going to be moving to the left and until I reach this relative humidity of 100% or saturated air point. And then if I'm not done, I'm going to keep moving more to the left along the curve of saturation as such until I finally remove 20 kilojoules of energy out of that air. If I had to get to the saturation point, then point 2 is going to be there. Otherwise, it might be on the horizontal section of my curve. I don't know yet, so I'm just going to leave it empty. So it could be here. This could be point 2. Could be here. This could be point 2. I don't know yet. Okay, but at least I know what I'm shooting for. Okay. Are we ready to start answering some questions here quantifiably? Let's start with part A, the easy stuff. Size of the box. I think we've already talked a little bit about that, right? We know the specific volume that we have at steady state. So we should be able to use that to determine the size of the box, given that we have 1 kilogram of dry air in the mixture. The psychrometric chart properties are always in terms of mass of dry air. So part A, solution, let's get going. A, V1 is equal to 0.84 kilograms, meter cube, kg of dA. And so therefore the volume of the box is equal to V1 times the mass of dA, which is 1 kg of dry air. So therefore it's going to be 0.84 meter cube here. I'm skipping the step of substituting because I think it's pretty straightforward. And the volume of the box is the length of the box cube because it's a cube, tells us that. And so therefore the length of each side is going to be the cube root of 84 meter cube. And when you punch in the numbers, I think that's about 94.6 centimeters. I did this in the other class already. Check. There goes 10 points per final exam. So easy. Okay. Let's keep going. Is there condensate in the box at steady state? Say yes or no question. Okay, something that always breaks my heart is somebody that leaves these questions completely empty and says nothing. Others who do all sorts of analysis and simply answer yes or no without bothering to give any kind of explanations. Don't do either one of those, right? Let's answer questions with some engineering reasoning behind them here. So to answer that question, basically, we're trying to determine whether we end up here on our psych little sketch for point 2 or here. That's really what we are asking. And so in order to answer that, we're going to have to do that energy balance analysis. And the energy balance analysis is going to be based on three different steps. Since we know the total amount of energy that's being absorbed, that's going to be true for the steel, it's going to be true for the air, and it's going to be true for the steel to the air. So let's break it down into each of those parts. The energy analysis. So one for the steel, one for the air, and one for the air giving energy to the steel. So for the steel alone, we know that the total change in energy of the steel is equal to 20 kilojoules. That's given to us. And we know that that's equal to the mass of the steel times the specific heat of the steel times the change in temperature of the steel. Let's see, what do we know about the steel? Oh, well, the properties are given to us. So we know C. So that guy is done. Delta T is going to be the temperature of the steel at 2 minus the initial temperature of the steel, which is minus 10 degrees. So minus is a plus 10 degrees Celsius. So I don't know the mass of the steel, and I don't know the final temperature of the steel. One equation, two unknowns. Okay. Well, let's keep going. Let's look at what's happening to the air. For the air, I've got the exact same thing, right? The change in internal energy of the air must also be equal to 20 kilojoules. That's great. And as we said, because the pressure is constant, everything is approximately constant there. So this is approximately equal to the change in enthalpy of the air. And we should put that down as one of our assumptions here, because that's not exactly correct. Change in internal energy of the air is approximately equal to the change in enthalpy of the air, since P is constant and V is not changing that much. Delta V is small compared to delta U. Okay, that's a reason for making that assumption. Not a bad place to start. And because we're dealing with a psych chart, that looks like the mass of dry air times the change in specific enthalpy of the air, which is itself equal to the enthalpy of the air at 1. I should really say here that these are minus, right? The change in internal energy of the air is minus 20 kilojoules because the air lost 20 kilojoules. This is minus delta H. This is minus delta H. And so therefore, this is minus H2 minus H1, which is H1 minus H2. That's where I'm at this point. I did not spell that out. You guys should worry about spelling things out when you're doing things on your test and keeping things as clean as possible. Okay, well, we know this guy. because we looked it up initially, right? The starting point, that was this right there. So that's kind of nice. We're good with that. That's 39 kilojoules per kg of dA. We know this guy, that's 1 kg of dA. Oh, so that's kind of clean. So the only guy we don't know is this. Wow, one equation, one unknown. We're in great shape here, right? Are we good? Right, because our equation is 20, let's see, 20 kilojoules is equal to MdA H1 minus H2. And so that's equal to 1 kilogram times 39 kg per kg minus H2. And so what we are saying, therefore, is that H2 is equal to 39 minus 20, or 19 kilojoules per kilogram of dry air. Right off the bat. Okay. Okay. So back to our, at this point, we would look at the psych chart. I'm not going to close my screen here to go back to it. I'm just going to look at it myself. I know that I'm looking for an enthalpy of 19 kilojoules per kg. I'm following it down, and whoa, I see that I'm way below where I was initially. So in fact, I've answered that question here. I am not here. I am here. This is my point 2. And this guy here is at 19 kilojoules per kg of dA. Real convenient because I have 1 kg of dA. So the total enthalpy is equal to the specific enthalpy at that particular point. So that's my point. That's where I'm at. And just by looking at the psych chart at that point, I can immediately get, by going down, that I am at, looks like right about 5 degrees Celsius. So that tells me my final point. T2 is equal to 5 degrees Celsius, state 2. Phi is equal to 100%, right? I'm saturated still. V2, well, I'm not going to care about that. H2, although let's just check it out for fun here. 5 degrees Celsius, it looks like it's about 0.8, maybe 0.795. 0.795 meter cube per kg. H2 is 19 kilojoules per kilogram of dry air. And T2, most importantly, dry bulb, is equal to 5 degrees Celsius. And what about the wet bulb temperature?
It should be the same, right?
It should be the same because my relative humidity is 100%, exactly. So this is equal to T2 wet bulb, exactly. So I've got everything at that point. So this is an important observation here because I can go back now to my equation 1 when I'm saying that my air to the steel, so really what we were saying is at steady state, T of steel 2 is equal to T of air at 2. We're in equilibrium. per one of our assumptions. And so that means that I can now go back to my equation for steel and establish that 20 kilojoules is equal to the mass of steel times the acidic heat of steel, which I know, times 5 degrees Celsius plus 10 degrees Celsius, which is my only unknown at that point, is the mass of steel. By the way, to be more rigorous here, this is really Kelvin at that point, right? Because I'm looking at a delta T, which is going to be 15 degrees Kelvin. I want to emphasize this because big pet peeve of mine are people who multiply and add, multiply and divide by degrees Celsius, which is an offset scale. You don't do that. You can only multiply and divide by degrees Kelvin, which is an absolute temperature scale. And remember, this is a delta T that we're dealing with. So whether we're dealing with the offset scale of Celsius or absolute scale, it still is going to be the same change in unit. But let's be real clear, when we're going to divide through, we're going to be in degree Kelvin over there to be dimensionally consistent. And so we're going to solve for M by doing that. And that's part B of our problem. So part B is solved. Please box your solutions when you're done to be really clear what you're doing. Okay, so we answered A, B. C is, oh yeah, sorry, B, no, B was the, so this part, this here is answered part C. For part B, since point 2 is at a lower omega than 0.1, yes, we have condensation. Okay, and when I wrote down my state point at 2 here, I should have put down that condensation here. Let's check it out. I'll look it up for you here on my graph, and you guys verify this for yourself later. Looks like I'm at about 0.06. 0.006. A little bit less, 0.0055. Let's be a little bit more accurate here, 0.0055. Right, so we went from 0.0075 to 0.0055 kilogram of water per kg of dry air. Of course, the dry air hasn't changed. So that means that we lost 2 grams of water out of the air. That's how much condensate we have. Okay. The answer to this is omega 2 minus omega 1 times m of dry air, which is equal to, I'm sorry, 1 minus 2, which is 7.5 grams minus 5.5 grams per kg dA times 1 kg dA is equal to 2 grams of water condensed. And I think that's the last part of the problem that we actually needed to quantify here. Mass and temperature of the air in a box. Well, the mass of the air in a box is 1 kg since it's an isolated system. The temperature is 5 degrees Celsius. The temperature of all these things are going to be 5 degrees Celsius because we're in thermal equilibrium. Put that down in our assumptions. Mass of the liquid water is 2 grams. The mass of the water vapor, well, it's whatever I had at the beginning minus what I lost. So this is going to be 5.5 grams. And at the very end, mass, temperature, pressure, total enthalpy of the gas mixture in the box. Well, we squeezed out 2 grams out of everything else. So we start off with 1 kilogram of dry air and 7.5 grams of water. So we're going to end up with 1.0055 kilogram of mixture. The pressure hasn't changed. It's still 1 atmosphere. The enthalpy of that mixture is 19 kilojoules per kg of dry air. The temperature, wet bulb, dry bulb, is 5 degrees Celsius and 5 degrees Celsius. And the relative humidity is 100%. It's so easy, really, at the end when you're looking at the psych chart, isn't it? And I think we've answered every part. And really, even with all the talking of everything we did, it took like 20, 25 minutes. So if you're in a test environment, you know, that gives you a lot of time for organizing your work and keeping everything clean and making your presentation unambiguous, I think. Spend a little bit more time on highlighting the assumptions you're making to make sure that it's all really clean. Like, for example, we have assumed that the volume of the steel doesn't affect anything in the box. Volume of steel is negligible. We've also assumed that the energy of liquid water is negligible. I think once you have 4 or 5 assumptions that are reasonable, it's all good. All right. Well, we're just a little over time here. Any questions or comments?